Hello students, welcome to Alpha's e-learning. We are discussing ethers and this is session 71. In previous session was learned that methods of preparations of ethers along with physical properties, and we also learned what type of chemical properties ethers can be shown. Means similar to alkanes, ethers are also having very less reactivity. Just like ethers are also derivatives of alkanes, just like alkanes, ethers also shows less properties. Means compared to alcohols, ethers chemical properties are less, we can say. In case of alcohols, reactive sites are more, like OH bond, by breaking of OH bond, by breaking of CO bond, we learn like that. But in case of ethers, here by breaking of OC bond, that happens under drastic conditions. Let us see the properties in which way ethers are going to react. In the first one, chemical properties of ethers. In that first one is halogenation. I used to consider diethyl ether, CH3, CH2, O, CH2, CH3. This one is symmetrical ether because of both alkyl groups are ethyl groups. Here this carbon, generally what we are calling alpha, and this carbon is beta with respect to OR, functional group means OR group. Here this carbon is alpha and adjacent carbon is beta. And because of symmetrical ether, this carbon is also alpha and this carbon will be beta. In order to distinguish these two alpha carbons, one we are going to name as alpha dash and this one we are going to name as beta dash. So in ethers, diethyl ether, there are two carbon containing alkyl group that we are designated as alpha beta and alpha dash beta dash. Diethyl ethers upon halogenation in presence of dark. Halogenation, chlorination in presence of dark. In presence of dark, reaction takes place. Which type of reaction? Free radical substitution reaction. Here, free radical substitution reaction will be in control. As a resultant, we are getting mono-halo ethers. So that halogenation preferably takes place at alpha carbon. Halogenation preferably takes place at alpha carbon. Then what product we are getting here is CH3, CH2, OCHCl and CH3. This is what we call alpha chloroether. And here HCl eliminated. Now, this one further reaction with chlorine and dark. Then we are getting second halogenation takes place at this alpha carbon. Means CH3, CHCl, O, CHCl, CH3. This is what we call alpha dash dichloro diethyl ether. Alpha dash dichloro diethyl ether. Free radical substitution upon monohalogenation, alpha carbon containing hydrogen replace, HCl eliminated. What number of chlorine molecules are going to participate? The same number of HCl molecules are going to eliminate. And which upon further reaction with chlorine in presence of dark, we are getting alpha dash. Means again at alpha carbon. So alpha dash dichloro diethyl ether. This reaction in general we are going to mention in presence of dark, means in absence of sunlight. So what happened in presence of sunlight? In presence of sunlight, if you observe the reaction, CH3, CH2, OCH2, CH3, diethyl ether upon reaction with chlorine in presence of sunlight. Here 10 moles of chlorine is going to react with diethyl ether and we are getting Cl5C2. Instead of C2H5, all the hydrogens are replaced by halogen atoms. So C2Cl5, O C2Cl5. This is what we call Parahaloether. So parahalo means thoroughly halogenated, means completely halogenated, means there is no more hydrogen remains here. All the hydrogens are replaced by halogen atoms. That's what we call parahaloethers. So diethyl ether upon reaction with 10 moles of chlorine, we are getting parahaloether by elimination of 10 moles of HCl. So substitution reaction, first type of chemical properties, side chain halogenation or alkyl group halogenation, during halogenation in presence of the monohalogenation at alpha carbon, which upon further halogenation we are getting alpha dash dichloro diethyl ether. But the same halogenation if performed in presence of sunlight, then we will get parachloroether. Parachloro means thoroughly fluorinated, means all the hydrogens are replaced. And second one is combustion. As we know very well, all combustion reactions are oxidation reactions. All combustion reactions are oxidation reactions because that reaction takes place in presence of excess of oxygen. Just like alkanes upon combustion gives carbon dioxide and water, just like alkanes upon combustion gives carbon dioxide and water, ethers also undergoes combustion gives carbon dioxide and water. So C2H5, OC2H5, diethyl ether undergoes combustion in presence of excess of oxygen. Here we are getting CO2 and H2O. Total 4 carbon atoms are there, 4 CO2. Total 10 hydrogen atoms are there, 5 H2O. 4 to the 8 plus 5, 13. But here one oxygen is there, still 12 requires. So 1 mole of ether undergoes combustion with 6 moles of oxygen, and we are getting carbon dioxide and water. Next one, oxidation means so far whatever we learn, that one is based on this alkyl groups, properties based on alkyl groups. Now second type of reactions, this second type of reactions based on oxygen, either containing oxygen. So in the first one, oxidation. First one is oxidation. Ethers undergoes oxidation. Ethers undergoes oxidation in presence of sunlight. It gives peroxoethers. Let us see. C2H5, OC2H5. Here oxygen possesses 2 lone pairs. This one upon oxidation in presence of sunlight, here we are getting ethyl peroxide. C2H5, OC2H5. Here two lone pairs are there at this oxygen, and here nascent oxygen which possesses with 3 lone pairs means 6 electrons. Now this one acts as Lewis acid and this oxygen acts as Lewis base. So either oxygen donates electron pair to vacant orbital of nascent oxygen, then there will be a formation of covalent bond. Right now central oxygen possesses only 1 lone pair, and this terminal oxygen possesses 3 lone pairs. This is what we call ethyl peroxide. This is what we call ethyl peroxide. So diethyl ether or ethers undergoes oxidation. Ethers undergoes oxidation in presence of sunlight, and we are getting ethyl peroxide. Ethyl peroxide is heavy liquid, pungent smell, explosive, unstable. Heavy liquid, pungent smell, explosive, unstable. So ethyl peroxide, because of it is explosive, we need to remove that oxygen. In order to remove that oxygen, ether in general going to shake with ferrous sulfate solution. Ferrous sulfate solution. Ferrous sulfate solution, because of it oxidized by that oxygen peroxide. That means it converts into unstable ethyl peroxide into ether. Ethyl peroxide into ether. Which one converts? Ferrous sulfate. Nothing but ferrous sulfate protects. Or we can also use Ki, potassium iodide. Since I- is a strong reducing agent, By taking that oxygen, it converts into I2. That means ethyl peroxide. Ether undergoes oxidation in presence of sunlight. We are getting ethyl peroxide. This ethyl peroxide is highly unstable, heavy liquid, explosive, pungent smell. So because of its highly unstable, it is explosive, we need to remove that oxygen. That's why either directly never try to drain us, because it may leads explosion. So what happened? In order to remove that peroxide, which reagents in general we have to use? Either ferrous sulfate solution or potassium iodide or sulfuric acid also we can use. So when we are using any of these, what happened? That oxygen is taken by these compounds. Ferrous sulfate converts into ferric sulfate. Ki gets oxidized into I2, and H2SO4 also gets oxidized to permonosulfuric acid, like that it converts, which is not explosive. So in order to prevent formation of ethyl peroxide, in general we have to use cuprous oxide. I am repeating, to prevent formation of ethyl peroxide, we are using cuprous oxide Cu2O. And if once formed, in order to remove that oxygen, in order to convert that ethyl peroxide into diethyl ether, means in order to convert that explosive ethyl peroxide into diethyl ether, we have to use ferrous sulfate solution KIR H2SO4. For prevention of formation of ethyl peroxide, we have to use cuprous oxide. The same oxidation takes place with a strong oxidizing agent. Strong oxidizing agent like potassium dichromate. With potassium dichromate, diethyl ether oxidized to aldehyde. Diethyl ether oxidized undergoes oxidation in presence of potassium dichromate, strong oxidizing agent. In presence of strong oxidizing agent, diethyl ether gets oxidized to aldehydes. 2CH3CHO is aldehyde. But since potassium dichromate is oxidizing agent, strong oxidizing agent, it also further oxidizes to carboxylic acid. That means in presence of potassium dichromate, diethyl ether oxidizes first to aldehyde, but which upon further oxidation it converts into carboxylic acid. Next one, with mineral acids. Diethyl ether forms salts with mineral acids. Mineral acids means inorganic acids like HCl, H2SO4. With mineral acids, diethyl ether forms salts. That salts what we call oxonium salts. Formation of oxonium salts. Oxonium salts. Let us see reaction. ROR ethers, they have tendency to donate the lone pair of electron. Because of the presence of lone pair upon oxygen in ethers, this acts as Bronsted-Lowry bases. Bronsted-Lowry bases, also called Lewis base. Ethers acts as base. Which type of base? Bronsted-Lowry base means they can accept the proton, and Lewis base, they will accept proton by donating its lone pair. Because of they have tendency to donate lone pair of electron, we can say Lewis base, and because of they have tendency to accept the proton, that's why we can call Bronsted-Lowry base. Now, ethers upon reaction with HCl, then we are getting ROR, H plus and Cl minus. First of all, we should remember one point. This ability means tendency to donate the lone pair of electron is less for heavy alkyl group containing ethers. Means more the number of carbon atoms, as we discussed in previous sessions. Because of steric hindrance, more steric hindrance, it prevent the donation of electron pair. That's why its a tendency to show basic nature also decreases. Now, here simply instead of dimethyl ether, ethyl methyl ether and diethyl ether, up to there okay. ability to form oxonium salts. And moreover, these oxonium salts are stable only at low temperature. These oxonium salts are stable at only low temperature. With increasing temperature, their stability decreases. With increasing temperature, their stability decreases. So let us sketch the diethyl ether C2H5O C2H5 upon reaction with HCl. It forms C2H5 C2H5 OH plus and Cl minus. Similarly with H2SO4 H2SO4 C2H5O C2H5H plus along with that HSO4 minus. See here we know very well ethers are insoluble in water, but salts are soluble in water. Ethers are insoluble in water, but salts are soluble in water. Right now, ether forms salts. Which type of salts as mentioned? Oxonium salts. Ether forms oxonium salts. Because of ethers can form oxonium salt with mineral acid at low temperature. These means oxonium salts are soluble in water. Oxonium salts are soluble in water. That means if we want to separate, say one is alkali halide, another one is ether. We are having a mixture of two organic compounds of which one is ether, another one is alkali halide. And here when we mix with HCl or H2SO4, any mineral acid, then ethers forms oxonium salts, and these are soluble in water. It comes into aqueous layer. And whereas remaining other organic compound like alkyl halide, it still remains there only, or it will goes to organic layer. That means mixture of compounds we can separate. By using mineral acid due to formation of oxonium salts. Now, these oxonium salts upon washed with water, distilled with water or washed with water, again you will get ethers. Means that proton will be transferred to water molecule. So the ability to form oxonium salt decreases with increase in temperature, decreases with increase in number of alkyl groups in ether. So in all these reactions it is very clear, oxygen donates electron pair to H plus. That means there will be formation of coordinate covalent bond in between ether, oxygen and proton, right? Now formation of coordinate covalent bond not only with mineral acids, but also with the electron deficient species, means with Lewis acids. Let us see, diethyl ether is able to form coordinate bond with boron trifluoride BF3, AlCl3, all these are Lewis acids. So oxygen donates electron pair into vacant orbital of boron. That means it forms adduct, ethers forms adduct. Now let us recall tetrahydrofuran. Here oxygen possesses two lone pairs. As B2H6 diborane, it exists. Borate exists as diborane. BH3 does not exist, and it exists as B2H6. But when we place in BHF, because of BHF also cyclic ether, and this ether is going to donate electron pair into vacant orbital of boron BH3, hence there will be formation of adduct. Hence B2H6 means dimer exists as monomer in THF. Not only here, and whenever we are going to use Grignard reagent, always we have mentioned that solvent is ether. In case of Grignard reagent, why we preferably use as ether solvent? Let us see. We know that Grignard reagent means RMGX Grignard reagent, and here this magnesium is coordinated with ether oxygen. Magnesium is coordinated with ether oxygen. That means ether oxygen always prefers to form coordinate covalent bond with electron deficient species. In case of Grignard reagent, as we know, this one is R minus, magnesium bears positive charge, being metal it bears positive charge. Towards that positively charged magnesium, ethers are going to donate electron pairs. Next property is reactions involving cleavage of CO bond. Ethers undergoes hydrolysis. Undergoes hydrolysis in presence of acids at high pressure and temperature. Let us see. ROR ethers undergoes hydrolysis in presence of acid H plus. We are getting alcohol. This is nothing but reverse reaction from dehydration of alcohols. Alcohols upon dehydration will end formation of ether, and now ether upon hydrolysis we are getting alcohols. But if it is symmetrical ether, just like dimethyl ether CH3OCH3, which undergoes hydrolysis H plus, initially it forms oxonium saltide CH3OCH3 and H plus. As I mentioned that these are stable at low temperature. With increasing temperature, what happens? Stability decreases. Then what happens here? Oxygen of water molecule attacks upon this carbon, and this bond electron pair shifted towards positively charged oxygen. Resultant we are getting CH3OH and CH3OH2 plus. Later this one is going to lose proton to water solvent, and we are getting CH3OH. So in case of symmetrical ether, we are getting only one alcohol. Just like in case of dimethyl ether, we are getting methyl alcohol only. And one more thing here, this reaction is SN2 reaction. SN2 reaction, substitution, nucleophilic biomolecular, because they are without formation of carbocation. Let us consider C2H5OCH3. This one upon first in presence of acid formation, then we will get C2H5OCH3 and H plus. So here first OH plus formation takes place. Later water molecule has to, means solvent molecule has to attack. Now where it will attack? Because there are two possibilities are there. This oxygen lone pair will attack upon this carbon, further this electron pair will be shifted towards positively charged oxygen, that is case 1. And case 2, this lone pair may attack upon this carbon, further these electrons will shift towards the positively charged oxygen. So where that incoming, means the solvent molecule prefer to attack, that is the one which consists less hindrance. That means solvent molecule prefers to attack upon less hindered alkyl group. In other words, small alkyl group. We are out of ethyl and methyl. Where it will attack? Upon methyl because of less hindrance. So this one is correct and this one is wrong. Again, this one is SN2 mechanism. Remember that in SN2 mechanism only we need to consider which one is small and which one is large, and preferably solvent molecule attacks upon small alkyl group rather than large alkyl group. But in case of SN1 that is different. I will discuss now. So now water molecule attacks upon this carbon, these electrons will be shifted. So C2H5OH plus CH3OH. So water it may be, you are getting alcohol only, no? Yes, we are getting alcohol only. Now let us see the same example with C2H5OCH3. Here I am going to use O18. This one upon H plus and H2O. Try to write the product and find out where that O18 will go. Means it comes along with ethyl alcohol and it comes along with methyl alcohol. Next one, C2H5OCH3. Here H plus, I am going to use O18. In this case, you are getting same product or different products in both the reactions. Try to check out. And I am going to consider one more example. That is, say R, CHR, OR. That means Here this alkyl carbon is secondary carbon, this one is primary. So one is primary, another one is secondary. This one upon treatment with H plus, we will get OH plus RCHR OH plus. Now, because of the secondary carbocation, its formation is feasible or possible. Its formation is feasible or possible. In such a case, this CO bond is going to break. Earlier, with CO bond, as I mentioned, here small alkyl group. With this small alkyl group, CO bond is going to break. But here, which one? With the large alkyl group. In this case, what we are getting? RCH plus R plus ROH. Say it is R dash. That means we are getting R dash OH. Later, upon this carbocation, water molecule has to come and attack. Further, we are getting OH and R. So, which bond will be here? If alkyl group is able to form stable carbocation, whether it is secondary or tertiary or benzyl or allyl, whatever it may be, ultimately, if it is able to form stable carbocation, then here this CO bond is going to break instead of this CO bond breaking. Hope you got the point here. In this case, because of carbocation is unstable, that's why after attacking of a solvent molecule upon less hindered carbon, only CO bond breaking takes place. But in this case, what happened? Initially, first only CO bond breaking takes place, which leads formation of carbocation, and after formation of carbocation, solvent molecule has to come and attack. So this mechanism proceeds via SN1 mechanism. Let us see if this alkyl group is a tertiary butyl alkyl group. So tertiary group, this carbon is tertiary carbon and this one is primary. So tertiary butyl and methyl, like that, let us consider this one upon reaction with H plus, we are getting RCR, here O, oxygen, and it gives positive charge CH3. Now which bond will break? So possibility number one, solvent molecule has to come and attack upon this carbon, or this bond has to break. So if it is able to form stable carbocation, here if it is able to form stable carbocation, because of this carbon is tertiary carbon and it is able to form tertiary carbocation, resultant what we are getting? R3C plus CH3OH. So after formation of carbocation, that's why it proceeds via SN1 mechanism. So attacking of solvent molecule, resultant we are getting CR3COH. So which CO bond is going to break? That depends upon which alkyl group is present. If a bulky alkyl group is there and which is able to form stable carbocation, in such a case we can say that CO bond is going to break. Whereas in case of small alkyl groups like this, what happened here? The one which is less hindered, that carbon oxygen bond is going to break. Let us see these examples. So far whatever we discussed, let us apply the same concept here. This one is a methoxybenzene, also called enizone. Enizone upon treatment with D plus, not H plus, D plus, later which upon treatment with water H2O. Let us see. First we are getting oxygen gets protonated, of course here OD plus we are getting CH3. Then what we expected here? So here is it able to form any carbocation, methyl carbocation or phenyl carbocation, both are unstable. Hence in such a case, water molecule prefers to attack upon less hindered alkyl group, then this bond is going to break and this OC bonded electrons are shifted towards positively charged oxygen. This mechanism, what do you say? SN2 mechanism, right? Then what product we are getting here? So OD deuterophenol plus CH3OH. Alright. Now let us see. I used to consider tertiary butyl phenyl ether, which upon protonation. So what we are getting here? Oxygen OH plus and CH3 and CH3. In such a case, which bond is going to break? here this CO bond, because of this carbon is tertiary carbon and tertiary carbocation can be stabilized. That's why this OC bond breaking takes place. Then we are getting phenol. We are getting phenol OH and tertiary butyl carbocation CH3, CH3, CH3 plus. And further we are using D2O, not H2O. Then D2O molecule oxygen containing one pair attacks upon this carbon, tertiary carbon, resultant we are getting CH3 taken twice COD, deuterotertiary butyl alcohol. See, in first case OC bond before OC bond is not going to break here, and first solvent molecule attacks upon less hindered alkyl group, then OC bond cleavage. And in second example, first OC bond cleavage and after formation of carbocation, this mechanism what we call SN1 mechanism, via formation of carbocation. And via formation of carbocation means again you may get a mixture of products that depending upon whether they propose rearrangement or not. Next, this one here H plus, we are getting this oxygen gets protonated and methyl group here plus. Now which OC bond